Tonight, Voyager 1 is moving through a place no human-built machine had ever reached before August 2012. It is more than 18 billion kilometers from the Sun, when something strange begins to happen. The stream of lower-energy particles that had surrounded the spacecraft for years suddenly collapses. At nearly the same time, higher-energy particles coming from beyond the Sun's protective bubble surge upward. Yet the magnetic field does not swing into the new direction many scientists expected. One set of measurements says Voyager has crossed, another seems to say it has not. And the strangest part is that there is no wall, no flash, no visible horizon. The spacecraft passes an invisible frontier at roughly 121.7 astronomical units from the Sun, and humanity does not immediately know that the crossing has happened. That is the mystery we are following tonight. What physically changed when Voyager 1 entered interstellar space? And how could scientists prove it after the most obvious instrument for the job had already failed decades earlier? By the end of tonight, that crossing will become something you can feel. If you enjoy calm journeys into the edges of known science, you can subscribe. Now, we follow the signal. Far behind Voyager, the Sun still looks like the star that built almost everything in the spacecraft's past. Its light has weakened with distance, but light is not the main thing that defines the region Voyager is leaving. The important boundary is made by moving matter. The Sun does not simply shine. It also throws out a continuous flow of charged particles called the solar wind, close to the Sun. That wind races outward at hundreds of kilometers per second. It fills interplanetary space, carries the solar magnetic field with it, and pushes against the thin material between the stars. For decades, Voyager 1 had been traveling inside that flow. But the solar wind cannot expand forever without resistance. Far from the planets, it encounters interstellar gas, plasma, magnetic fields, and energetic particles that belong not to the immediate solar environment, but to the local material through which the Sun itself is moving. The result is a vast bubble around the Sun called the heliosphere. You can picture it, imperfectly, as an enormous moving cavity pressed into the surrounding interstellar medium. Inside, conditions are dominated by the Sun's outflow. Outside, conditions are dominated by the material between stars. The outer surface separating those regimes is called the Heliopause. That was the frontier Voyager was approaching. The simple expectation was powerful because several independent things ought to change near the same place. Solar particles should fall away. Galactic cosmic rays arriving from outside should become more abundant. The plasma environment should become denser, and the magnetic field, shaped differently on either side of the boundary, might change direction. If all of those measurements shifted together, the crossing would be obvious. But nature did not make it obvious. As Voyager approached the boundary in 2012, its particle instruments began to report a region that behaved almost like a door being opened and closed. On July 28th, the abundance of particles associated with the heliosphere dropped sharply. At the same time, energetic particles from outside increased. It looked like the spacecraft might have reached interstellar space. Then the old environment returned. A few days later, the pattern happened again. This matters because a clean boundary is easy to imagine. You are inside, you cross one surface, you are outside. But Voyager's measurements suggested something more dynamic near the edge, a region in which magnetic structure could allow particles to leak in one direction while others escaped in the opposite direction. The spacecraft was not seeing a painted line across space. It was moving through a physical system. Then came August 25th, 2012. The lower energy particles linked to the solar environment dropped dramatically and did not recover. Higher energy cosmic rays from outside rose and stayed high. This time the change held. If you were sitting beside Voyager's detectors, looking only at the particle counts, the meaning would feel almost unavoidable. The population surrounding the spacecraft had changed. Material that had been common inside the Sun's bubble was disappearing. Material arriving from the galaxy was becoming dominant. The boundary appeared to be behind Voyager. But one measurement refused to cooperate. The magnetic field direction did not make the dramatic turn scientists had anticipated. That created a genuine physical problem. If Voyager had entered interstellar space, why did the field still point in nearly the same direction it had inside the heliosphere? And if Voyager had not crossed, why had the particle environment changed so completely and permanently? The disagreement was not a technical footnote. It changed what scientists were willing to claim. They needed another test. The most direct test would have been to measure the density and temperature of the plasma around the spacecraft. Interstellar plasma should be considerably denser than the extremely tenuous plasma near the outer edge of the heliosphere. If Voyager could measure that density directly, scientists could decide which environment actually surrounded it. But Voyager 1 had a problem that began 32 years earlier. Its plasma science instrument had stopped providing useful measurements after the 1980 Saturn encounter. The instrument was designed to directly study streams of charged particles. Now, at the one moment when a clean plasma measurement could settle the most important boundary crossing in the mission's history, that direct capability was gone. A machine launched in 1977 had survived Jupiter, Saturn, decades of radiation, cold, power loss, and distance. Yet survival alone was not enough. An instrument does not have to destroy a spacecraft to reshape a scientific question. It only has to stop working before the crucial measurement arrives. So Voyager had crossed into a new state before the team could prove what that state was. That is where the story becomes more interesting than a simple milestone. Because the heliopause was not defined by a commemorative distance, it was defined by physics, the team could not declare interstellar space merely because Voyager was very far away, or because one dramatic graph looked persuasive. They needed a measurement that discriminated between two competing explanations. Either Voyager was still inside an unusual outer layer of the heliosphere, where particles could exchange across magnetic connections without the spacecraft truly crossing the heliopause, or it was already outside, immersed in interstellar plasma, while the magnetic field happened to remain unexpectedly aligned with the field inside. Those are very different pictures, and distance alone cannot choose between them. Voyager kept moving. Every second carried it roughly another 17 kilometers farther from the Sun. Every day increased the separation by nearly 1.5 million kilometers. But even at that speed, nothing visible appeared ahead. There was no glow marking the next environment. No camera could turn around and photograph a boundary behind it. The evidence had to come from fields and particles. For months, space spacecraft continued returning measurements across billions of kilometers of radio distance. The signals arriving at Earth were extraordinarily faint. Yet within those data, scientists were waiting for one clue that could reveal the density of the material surrounding Voyager without using the dead plasma instrument. What they needed was a way to make invisible plasma announce itself. And, unexpectedly, the thing that would provide that test did not come from interstellar space at all. It came from the Sun Voyager had just left behind. The difficult part about finding the edge of the Sun's influence is that there is no single thing called the edge. Sunlight does not stop there. Gravity does not stop there. The planets do not stop belonging to the solar system. Even the Sun's magnetic influence does not vanish in one clean step. What scientists were looking for was something more specific, the place where the outward pressure of the solar wind finally lost control of the local environment. By the time Voyager 1 was approaching that region, researchers already had a broad physical picture of what should happen. Closer to the Sun, the solar wind moves outward at supersonic speed. It is thin, hot, electrically charged, and magnetized. As it travels, it expands into an ever larger volume of space. That expansion lowers its density and reduces its pressure. Eventually, the wind becomes too weak to push freely against the surrounding interstellar medium. The first major transition happens at the termination shock. Voyager 1 crossed that shock in late 2004, at a distance of about 94 astronomical units from the Sun. There, the solar wind slowed abruptly from supersonic to subsonic speed. The spacecraft had not yet reached interstellar space. It had entered a thick outer region of the heliosphere called the heliosheath. That distinction mattered. The heliosheath was still solar territory in the physical sense that the plasma had originated from the sun, but it was no longer behaving like the fast solar wind closer in. It had been compressed, heated, slowed, and diverted as it approached the surrounding interstellar material. So by 2012, Voyager was not searching for the first sign that the solar wind had changed. That had happened years earlier. It was searching for the next transition. The heliopause. The simplest model treated this boundary as the surface where solar plasma on one side met interstellar plasma on the other. The two populations were expected to have different densities, different particle distributions, and magnetic fields shaped by different environments. That gave scientists several independent signatures to watch. The first was the population of energetic particles born inside the heliosphere. Voyager's instruments were detecting lower energy particles that had been accelerated within the outer solar environment. As long as the spacecraft remained inside the heliosphere, those particles should remain relatively abundant, cross the heliopause, and their behavior should change. They could no longer be trapped in the same way by the solar magnetic environment. Their counts should fall sharply as Voyager moved beyond the region that produced and confined them. That was one expected marker. The second involved particles moving the other way. Galactic cosmic rays come from beyond the solar system. Many originate in violent processes elsewhere in the galaxy and travel for enormous distances before reaching our neighborhood. The heliosphere does not stop all of them, but it does act as a partial shield. The outward flowing solar wind and a magnetic turbulence embedded within it scatter and deflect many incoming charged particles. That means cosmic ray intensity generally increases as a spacecraft travels farther outward through the heliosphere. Near the heliopause, scientists expected that shielding effect to weaken dramatically. Outside the boundary, Voyager should encounter a higher and more stable population of galactic cosmic rays. So one particle population should drop, another should rise. If both happened at nearly the same moment, the case for a crossing would become much stronger. But particles were only part of the prediction. The third signature was plasma density. Inside the outer heliosphere, the solar wind had expanded across an immense volume, leaving the plasma extremely tenuous. The interstellar plasma outside was expected to be denser, not dense in any everyday sense. Even the interstellar medium is a near vacuum by terrestrial standards, but the difference between the two environments should still be large enough to measure. The expected contrast was not subtle. If Voyager moved from the heliosheath into the local interstellar medium, the number of free electrons surrounding the spacecraft should rise substantially. That meant density could become a decisive test. Unlike a change in one particular class of energetic particles, plasma density spoke directly to the material filling the region itself. Then came the magnetic field. This was where the picture looked especially clean on paper. Inside the heliosphere, the sun's rotating magnetic field is carried outward by the solar wind and stretched into a vast spiral pattern. Outside, the interstellar magnetic field belongs to the surrounding galactic environment. Those fields did not have to point in the same direction. So scientists expected that crossing the heliopause could produce a noticeable change in magnetic field orientation. Imagine moving from a river into the sea and watching the current rotate around you. If the particle populations changed, the plasma became denser, and the field direction also shifted. Then three independent systems would tell the same story. That was the ideal crossing. And that ideal shaped how scientists interpreted everything Voyager sent back. This is important because measurements do not arrive without expectations. A detector can report a number, but the meaning of that number depends on a physical model. If the model says several quantities should change together, and only some of them do, the disagreement becomes evidence in its own right. By 2012, Voyager was already moving through a region that refused to fit the clean version. The solar wind itself had become difficult to track directly. The heliosheath was changing. The magnetic environment was becoming more complicated, and the particle populations were beginning to behave as though the boundary was becoming porous before the spacecraft had clearly crossed it. That possibility was physically plausible. Charged particles do not move through space like tiny billiard balls crossing a painted border. Their paths are controlled by magnetic fields. If field lines near the heliopause connected regions on opposite sides, particles could leak across those connections without the spacecraft itself fully entering interstellar plasma. That would make the boundary look less like a sealed shell and more like a changing magnetic interface. And if that happened, a rise in cosmic rays alone would not prove the crossing. A fall in solar particles alone would not prove it either. The team needed the signatures to be interpreted together. That created a stricter standard than distance or drama. Voyager could not simply become interstellar because it had travelled farther than anything before it. The environment had to demonstrate that the governing plasma had changed. By the middle of 2012, the spacecraft was approaching 122 astronomical units from the Sun. A radio signal from Earth needed well over 16 hours to reach it one way. Commands and responses therefore unfolded across more than a day, even before anyone began interpreting the data. Yet the real delay was not communication. It was physics. The spacecraft was entering a region where different measurements might not change at the same place or at the same time. That possibility mattered because nature was about to separate the expected signatures. First, the particle populations would begin to switch. Then they would switch back. Then they would switch again. And instead of a clean doorway, Voyager would find something that behaved like a boundary, opening in pieces. The first serious break came in late July. For a moment, the particles surrounding Voyager looked as though interstellar space had arrived. Then, the old environment returned. The first warning came before anyone was ready to call it a crossing. On July 28, 2012, Voyager 1 was moving through the outer heliosheath when its particle instruments recorded a sudden change. The lower energy particles associated with the heliosphere began to drain away. At almost the same time, the intensity of galactic cosmic rays arriving from outside increased. For a moment, the pattern looked exactly like the beginning of interstellar space. Then it reversed. The particles from inside returned. The cosmic ray intensity eased back toward its previous level. Voyager had not simply crossed a permanent frontier and continued outward. Something near the boundary had changed around it. That was the first clue that the heliopause might not behave like the clean surface imagined in the simplest diagrams. A diagram has to draw a line. Plasma does not. Charged particles respond to magnetic fields, and magnetic fields can connect regions that are physically separated. If field lines near the heliopause opened pathways between the heliosphere and interstellar space, particles could move along them even while Voyager remained on one side of the true plasma boundary. That could explain the strange exchange. Particles originating inside the heliosphere could escape outward. Galactic cosmic rays could enter more easily. Voyager would then detect an environment that looked partly interstellar without necessarily being immersed in interstellar plasma. The idea became easier to picture if you stop imagining the heliopause as a wall. Imagine instead a network of invisible rails. A charged particle does not simply choose any direction it wants. In a magnetic field, its motion is strongly organized around field lines. Change the magnetic connection, and you change where those particles can travel. For years inside the heliosheath, many energetic particles have been effectively trapped and scattered through the solar magnetic environment. Near the outer edge, that confinement began to weaken. The July event suggested that Voyager had found a route through which particles could suddenly exchange. Then the route seemed to close again. A second abrupt change followed in August. Again, heliospheric particles dropped. Again, cosmic rays increased. Again, the pattern did not yet remain permanent. Instead of one clean crossing, Voyager was seeing repeated transitions. That made distance less useful than ever. The spacecraft was still traveling steadily outward, but the environment around it could change much faster than Voyager's physical motion alone could explain. The boundary itself could be structured. It could move. Magnetic connections could rearrange. Solar activity launched months earlier could distort conditions far beyond the planets. So when a detector changed sharply, the team had to ask a harder question than, how far has Voyager traveled? They had to ask, what physical state is Voyager in right now? That distinction is the heart of the crossing. On August 25th, the particle instruments changed again. This time, the change did not reverse. The population of lower energy energetic particles associated with the heliosphere collapsed. Some of these particles eventually fell to levels more than 1,000 times lower than those measured years earlier in the heliosheath. At nearly the same moment, galactic cosmic rays climbed to the highest intensities Voyager had recorded during its entire journey. Two populations moved in opposite directions. One vanished outward, the other flooded inward. And the new state stayed. You can feel why this looked decisive. Voyager had spent decades moving through material shaped by the sun. Now, almost suddenly, the particles characteristic of that environment were gone from its detectors, while particles from the galaxy were arriving with far less obstruction. If the Heliopause was the place where solar influence over the local plasma gave way to the interstellar medium, this was exactly the kind of transformation scientists had been waiting for. But the measurements contained a complication. The magnetic field became stronger. Its direction, however, did not rotate dramatically. That was unexpected. The clean prediction had been that the interstellar magnetic field would have a noticeably different orientation from the field carried outward by the Sun. If Voyager truly crossed into interstellar space on August 25th, the magnetic field should help confirm it. Instead, the field stayed surprisingly aligned with the direction observed just inside. That prevented the particle data from ending the argument. At the time, the Voyager team described the new region cautiously. They called it a magnetic highway. The name captured what the particles seemed to be doing. The field appeared to provide a pathway connecting the heliosphere with the outside. Energetic ions from within could stream away, while galactic cosmic rays could stream in. NASA initially described the August 25th environment as a depletion region or magnetic highway, where particles could travel into and out of the heliosphere along relatively smooth magnetic field connections. It looked like a final transitional region. Perhaps Voyager was still technically inside the heliosphere, but standing on magnetic lines that were connected to interstellar space. That interpretation preserved the magnetic field expectation. If the field had not rotated, perhaps the spacecraft had not crossed the heliopause yet. The particle changes could then be explained as leakage across an unusual boundary layer rather than proof of full entry into the interstellar medium. This was not scientists refusing an exciting conclusion. It was the opposite. The more historic the claim, the more important it became to separate a persuasive sign from a discriminating measurement. Voyager had produced an extraordinary result. But extraordinary did not mean complete. The spacecraft continued outward through the new particle environment. Days became weeks. The heliospheric energetic particles did not return. Galactic cosmic rays remained elevated. Whatever boundary Voyager had encountered on August 25th appeared durable. The door that had opened and closed earlier now seemed to have stayed open behind the spacecraft. And that persistence made the magnetic contradiction harder to ignore. If Voyager remained inside the heliosphere, how long could it continue through a region almost emptied of heliospheric energetic particles? If it was outside, why had the field direction changed so little? Both explanations now carried a cost. This is where a boundary becomes scientifically useful. A boundary is not important because it has a name. It is important because conditions on either side are governed differently. To identify the heliopause, scientists needed to determine not merely which particles could reach Voyager, but what material actually surrounded the spacecraft. That required plasma density. The local interstellar medium was expected to contain far more electrons per unit volume than the extremely rarefied outer heliosheath. A density measurement could therefore do what the magnetic direction had failed to do. It could distinguish between a strange solar-side boundary layer and the interstellar plasma itself. But there was still the problem inherited from 1980. Voyager 1's direct plasma instrument could no longer provide the measurement, so the team was left with a spacecraft sitting in an apparently new physical state, carrying strong particle evidence of a crossing, carrying magnetic evidence that seemed to resist that interpretation, and lacking the instrument that could most directly decide between them. For the moment, August 25th was not yet the historic date it would become. It was simply the day the particles changed for good. The proof would have to come later, from a completely different instrument. And before that proof arrived, the stubborn magnetic field would force scientists to live with an uncomfortable possibility. Voyager might already be in interstellar space without anyone being able to say so with confidence. By late August 2012, the argument was no longer about whether something important had happened. It was about what kind of event Voyager had actually crossed. The most dramatic evidence came from particles that had been part of Voyager's environment for years. Inside the heliosheath, the spacecraft had detected populations of energetic ions tied to the Sun's outer domain. They were not ordinary solar wind particles moving smoothly outward. Many had been accelerated, scattered, and trapped in the disturbed magnetic environment near the edge of the heliosphere. As Voyager moved outward, those particles had become one of the best markers of solar territory. Then, over a remarkably short interval, they nearly vanished. The change on August 25th was not a gentle decline stretched across months. The intensity fell sharply. For some particle energies, the drop eventually amounted to more than 3 orders of magnitude compared with earlier heliosheath levels. That means a signal that had once been common around the spacecraft became roughly 1,000 times weaker. At the same time, galactic cosmic rays moved the other way. These are high-energy charged particles arriving from beyond the heliosphere. They had been penetrating the Sun's magnetic bubble throughout Voyager's journey, but the heliosphere altered how many reached the spacecraft. As Voyager approached the edge, their intensity rose. After the August transition, it climbed to levels never before measured by the mission. One population collapsed, the other increased, and this time, neither returned to the old state. That permanence is what separated August 25th from the earlier episodes in July and August. Before the crossing, Voyager had experienced brief particle changes that looked like trial versions of what came later. Solar-associated particles decreased. Cosmic rays increased. Then the environment partially recovered. Those reversals told scientists that the boundary region could reorganize around the spacecraft. But after August 25th, the old particle population did not come back. Voyager kept moving outward at roughly 17 kilometers per second, and the new particle state remained. Think about the scale of that motion. In one day, the spacecraft traveled close to 1.5 million kilometers. In a week, it covered roughly 10 million. If the August change had been caused by a thin, temporary structure floating through the heliosheath, Voyager's continued outward motion should eventually have carried it into another region, yet the particle environment remained fundamentally altered. That made the crossing interpretation stronger with every passing day. The spacecraft was not merely brushing against a strange patch. It appeared to have left behind the particle reservoir that had defined the outer heliosphere. But the measurements were more subtle than a simple inside and outside switch. Charged particles are strongly shaped by magnetic geometry. A particle can disappear from a detector not because the plasma around the spacecraft has changed completely, but because the magnetic field has opened a path along which that particle can escape. That was why the team remained cautious. Imagine a room filled with smoke. If a door suddenly opens, the smoke can drain away quickly. Its disappearance tells you that the room is connected to somewhere else. But it does not, by itself, tell you that you have walked through the doorway. The particle data created a similar ambiguity. Heliospheric particles draining away showed that the magnetic confinement near Voyager had changed. Galactic cosmic rays rushing in showed that access from outside had increased. Together, those signals made the case powerful, but neither one directly measured the identity of the plasma physically surrounding the spacecraft. That distinction mattered because the heliopause is not defined simply by which energetic particles are present. It is the boundary between two plasma regimes. On one side, the material is dominated by the sun's outflow. On the other, the plasma belongs to the local interstellar medium. So the August particle changes could tell scientists that the magnetic environment had opened dramatically. They could strongly suggest a crossing, but the team still needed to know what medium Voyager was actually sitting in. Even so, the particle behavior revealed something important about the heliopause before the crossing was formally accepted. The transition could be extremely sharp. Voyager had spent years moving through the heliosheath after crossing the termination shock in 2004. That outer region stretched across billions of kilometers. Yet the final particle change happened over a comparatively tiny fraction of that distance. A spacecraft can spend almost 8 years traversing one broad transition region, then encounter a decisive particle shift in days. That contrast changes how you picture the sun's outer boundary. The heliosphere is enormous. The crossing itself can be narrow, and because Voyager was moving at only a few astronomical units per year, even a change unfolding over days corresponds to a surprisingly small physical thickness compared with the size of the heliosphere. This does not mean the entire heliopause is uniformly thin. Voyager measured one path through a dynamic, three-dimensional boundary, but along that path, the particle transition was abrupt enough to look less like a gradual fading of solar influence and more like a switch in magnetic access. That was the first major payoff. The sun's protective bubble did not simply dissolve slowly into interstellar space. At least in Voyager 1's measurements, some of its particle populations changed very quickly. And the second payoff was even larger. The heliosphere had been suppressing part of the galactic particle environment all along. Once Voyager moved beyond the region that strongly modulated those cosmic rays, the spacecraft suddenly experienced a more exposed version of the galaxy. Nothing visible changed. The stars did not brighten. The sun did not disappear. But the radiation environment shifted. You could think of the heliosphere as an invisible weather system around the solar system. It does not block every cosmic ray, and it is not a rigid shield, but it changes the charged particle climate experienced inside. Voyager had now moved into a region where that shielding was weaker. This made the crossing meaningful for more than navigation. For the first time, a working spacecraft was directly sampling the energetic particle environment beyond the heliosphere from the outside, rather than inferring it from within. But there was still one measurement refusing to align with the story. The magnetic field, its strength changed. Its direction did not rotate nearly as much as many models had suggested it should. That single mismatch prevented the particle evidence from becoming immediate consensus. The contradiction was now sharper than before. If Voyager had not crossed, the particle populations had somehow changed permanently while the spacecraft remained inside the heliosphere. If Voyager had crossed, then the magnetic field geometry at the heliopause was different from what many scientists had expected. Either way, something in the model had to give. And that is why August 25th did not end the investigation. It deepened it. The particles had made one thing difficult to deny. Voyager was no longer living in the same energetic environment. Now the stubborn magnetic field forced the next question. Could interstellar space begin without the magnetic field making the turn everyone had been waiting for? The particles had changed almost exactly as scientists hoped. The magnetic field had not. That single disagreement became the most uncomfortable part of Voyager 1's crossing. For years, researchers had expected the heliopause to separate two magnetic environments with noticeably different orientations. Inside the heliosphere, the solar magnetic field is carried outward by the solar wind, and stretched by the sun's rotation into a vast spiral. Outside, the local interstellar magnetic field belongs to the material moving through our galactic neighborhood. The geometry did not have to line up. So one of the clearest predicted signatures of interstellar space was a turn in the field direction. When Voyager reached the August 25th transition, however, that turn did not appear in the way many people expected. The field became somewhat stronger, but its direction remained surprisingly similar to the direction measured just inside the heliosphere. That was not a minor detail. It meant the crossing had produced a split verdict. The particle instruments were saying that the spacecraft had entered a new regime. The magnetometer was saying that one major expectation had failed. And this is where the story becomes less about a famous milestone and more about how science actually works. A model does not become wrong simply because one number disagrees with it, but the disagreement has to be explained. Perhaps Voyager had not crossed the heliopause at all. Perhaps it had entered a strange final layer inside the heliosphere where particles could escape along magnetic field lines connected to the outside. That was the conservative interpretation of it. Allowed scientists to preserve the expectation that the true heliopause crossing would still be marked by a stronger magnetic rotation later. The name Magnetic Highway fit that picture. Voyager might be standing on solar-side field lines that had become connected to interstellar space. Heliospheric particles could leak outward along those lines. Galactic cosmic rays could stream inward. The particle environment could therefore look dramatically different even though the spacecraft remained physically inside solar plasma. If that were true, then the missing magnetic rotation was not a contradiction. It was a warning that the real crossing had not happened yet. But there was another possibility. Voyager had crossed. The field outside simply happened to be aligned more closely with the field inside than the simplest models had predicted. That possibility was harder to accept immediately because it required changing the picture of the boundary itself. Instead of a clean magnetic turn, the heliopause near Voyager might preserve field direction across the transition. The particles could change abruptly while the magnetic orientation changed only slightly. If so, the model, not the spacecraft, was the thing that needed adjustment. Both possibilities could explain some of the data. That is why the magnetic field became so important. It was not merely another measurement. It was the measurement preventing premature certainty. For several months after August 2012, the Voyager team did not announce that the spacecraft had entered interstellar space. The caution was deliberate. The particle evidence was extraordinary, but the expected magnetic signature had not appeared. A historic claim could not rest on excitement alone. So scientists waited. Voyager continued moving outward, adding roughly 1.5 million kilometers of distance every day. The heliospheric particle population remained extremely low. Galactic cosmic rays stayed elevated. Yet the field direction still refused to provide the decisive turn. With every week, the two interpretations became easier to separate conceptually, but harder to distinguish observationally. If Voyager was still inside, then this final solar-side region was unlike anything the spacecraft had crossed before. If Voyager was outside, then interstellar magnetic geometry was unlike the simple expectation. Either way, the boundary had already taught them something. The heliopause was not behaving like a smooth surface in a textbook. It was a magnetic structure shaped by moving plasma on both sides. That matters because magnetic fields in space do not merely point somewhere. They store pressure. They guide charged particles. They bend, compress, drape, reconnect, and transmit disturbances. Near a boundary as large as the heliopause, the field is part of the architecture. The local interstellar magnetic field approaches the heliosphere, while the solar wind pushes outward from within. The two environments interact over enormous distances. Field lines can be distorted by that encounter before a spacecraft ever reaches the actual boundary. So the absence of a large rotation did not necessarily mean the two original fields were identical. The field outside could have been bent around the heliosphere. Imagine wind moving around a large rounded object. The flow immediately beside the surface does not preserve the same direction it had far upstream. It curves around the obstacle. Magnetic fields in plasma can behave differently from ordinary wind, but the physical idea of draping is useful. The interstellar field can be distorted as it encounters the heliosphere. If Voyager crossed where the draped interstellar field happened to align with the field inside, then the missing magnetic turn would no longer be mysterious. But that was still an interpretation. What the team needed was a test that did not depend on magnetic direction at all. They needed to identify the material surrounding the spacecraft. Solar-side plasma and interstellar plasma were expected to differ strongly in density. That density difference offered a cleaner discriminator. If Voyager was still in a magnetically unusual layer inside the heliosphere, the plasma around it should remain relatively tenuous. If it had crossed into the local interstellar medium, the electron density should be substantially higher. One measurement could therefore decide between two physical environments. And density had another advantage. It did not care which way the magnetic field pointed. It asked a simpler question. How many free electrons are here? That sounds straightforward, until you remember Voyager 1's condition. The spacecraft had been launched in 1977. Its original instruments were designed for encounters with Jupiter and Saturn, not for settling an argument at the edge of the heliosphere 35 years later. The instrument that could most directly measure the velocity, density, and temperature of plasma had stopped functioning properly decades earlier. Voyager's plasma science experiment had become unusable for this purpose after the Saturn era. That loss now became critical. The spacecraft had reached perhaps the most scientifically important plasma transition of its entire journey without a working direct plasma detector. It is difficult to design a better example of an engineering limit becoming a scientific limit. The boundary was there. The spacecraft was there. The distinction between the competing explanations depended on plasma density, and the obvious instrument was gone. Yet Voyager was not blind. Another surviving instrument could listen to plasma rather than directly collect it. The plasma wave subsystem measured electric field fluctuations in the surrounding charged environment. Under ordinary conditions, that did not automatically provide the density measurement scientists needed. The plasma had to oscillate strongly enough for the instrument to identify a characteristic frequency. And for that to happen, something had to disturb it. For months after the August transition, scientists did not have the signal. Then, far behind Voyager, the Sun produced the disturbance they needed. A powerful eruption launched a shock outward through the solar system. The shock would spend more than a year crossing the immense distance to the spacecraft. When it finally arrived, it would force the invisible plasma around Voyager to ring. And from that sound, scientists would learn which side of the boundary Voyager was really on. The missing plasma instrument did not leave Voyager 1 completely deaf to its surroundings. It changed the kind of question the spacecraft could answer. A direct plasma detector measures particles by letting them enter the instrument. From their number, direction, and energy, scientists can estimate quantities such as density, temperature, and bulk flow. That is the straightforward route when the instrument still works. Voyager 1 no longer had that route. But another instrument aboard the spacecraft had been designed for something different. The plasma wave subsystem did not count plasma particles directly. It measured electric field fluctuations across a pair of long antennas. In effect, it listened for the electrical motions that charged particles create when they move collectively. Usually, those motions are weak and complicated. But plasma has a useful property. Disturb it strongly enough, and its electrons can oscillate together at a natural frequency. That frequency depends mainly on electron density. More electrons in a given volume produce a higher plasma frequency. Fewer electrons produce a lower one. So if Voyager could detect a clear plasma oscillation, scientists could turn frequency into density. The problem was that quiet plasma does not automatically ring loudly enough to reveal itself. Something had to strike it. The needed disturbance began near the Sun. In March 2012, months before the August crossing, the Sun produced a powerful eruption. A large disturbance moved outward through the solar wind, carrying a shockwave across the solar system. Close to Earth, solar disturbances can arrive in days. Voyager was vastly farther away. The wave had to travel more than 100 astronomical units before reaching the spacecraft. 1 astronomical unit is the average distance between Earth and the Sun, roughly 150 million kilometers. At Voyager's distance, the disturbance was crossing a scale measured not in hours, but in months. The Sun had erupted while Voyager was still approaching the Heliopause. The consequence would not reach the spacecraft until the following year. That delay turned solar activity into an accidental experiment. In April 2013, Voyager's plasma wave subsystem began detecting a series of narrowband oscillations. The plasma around the spacecraft had started to ring. The signal was faint in human terms, but scientifically it was exactly what the team had been waiting for. This was not a sound travelling through air. There was no microphone recording a noise in space. The instrument was detecting electrical oscillations in the surrounding plasma, which scientists could convert into an audio-like representation for analysis and presentation. What mattered was the frequency. From that frequency, the electron density could be inferred, and the density was much too high for the outer heliosheath. The measured value was consistent with the local interstellar medium. That result changed the argument. Until then, the magnetic field had allowed 2 competing pictures to survive. One picture placed Voyager inside a strange solar-side region where particles could escape, while the field remained oriented much as before. The other placed Voyager outside the Heliopause, already surrounded by interstellar plasma, with the magnetic field unexpectedly aligned across the boundary. The plasma oscillation discriminated between them. If Voyager was still immersed in the tenuous plasma of the heliosheath, the oscillation frequency should have indicated a much lower electron density. It did not. Instead, the inferred density was more than 40 times higher than the plasma density measured in the outer heliosphere. That was not a small mismatch that could be hidden inside an uncertain model. It was a different physical environment. The surrounding material had changed. Now the particle evidence from August 2012 made sense in a new way. The disappearance of heliospheric energetic particles was not merely leakage from an unusual layer. The rise in galactic cosmic rays was not merely temporary access along connected magnetic lines. Voyager had entered plasma with interstellar density. The magnetic field had been the misleading expectation. Not because the magnetometer had failed. The instrument was working. The expectation about how much the field direction should rotate had been too simple for the actual geometry Voyager encountered. That is an important distinction. When an observation contradicts a prediction, the next step is not to choose the measurement you prefer. It is to find another measurement capable of separating the explanations. Voyager's plasma wave results did exactly that. And it did so through a chain of events no mission planner in 1977 could have scheduled. A spacecraft, launched for planetary flybys, survived long enough to approach the Heliopause. Its direct plasma instrument was no longer useful. A solar eruption left the Sun months before the crossing. The resulting shock crossed billions of kilometers. Then, in interstellar space, it compressed and disturbed the plasma around Voyager strongly enough for another surviving instrument to measure its natural oscillation. The failed instrument created a limit. The Sun supplied the workaround. But there was still a timing problem. The decisive plasma oscillation was detected in 2013. The particle transition had occurred in August 2012. If Voyager was definitely in interstellar plasma by April 2013, that did not yet prove the exact moment it had crossed the Heliopause. The spacecraft had travelled hundreds of millions of kilometers during the intervening months. Perhaps the true crossing happened later than August. Perhaps the particle transition marked only a magnetic boundary, while the plasma boundary came afterward. To establish the historic crossing date, scientists had to move backward through the data. They searched for earlier plasma oscillations. A weaker event had occurred in October and November 2012. It was less dramatic, but its frequency again indicated a density already far above what was expected inside the heliosheath. That moved the evidence closer to August. Then came the key inference. Plasma density was increasing gradually as Voyager moved farther outward. By tracking that trend backward, researchers could estimate where the density transition must have occurred. The answer converged on the same date that the particle instruments had already marked so sharply. August 25th, 2012. The crossing had happened months before the team could prove it. That is one of the most unusual features of Voyager 1's entry into interstellar space. Humanity crossed the Heliopause first. Recognition came later. For more than a year, the spacecraft kept transmitting while scientists assembled the physical case piece by piece. The historic announcement would eventually rest not on a photograph, not on a visible border, and not on a single spectacular detector spike. It would rest on consistency between different measurements taken at different times. Particles had changed abruptly. Plasma density was interstellar. The density trend pointed backward to the same transition. The magnetic field, once treated as the missing confirmation, became evidence that the boundary itself was more complicated than expected. And now the story could move to a deeper question. If the plasma outside the heliosphere was more than 40 times denser than the plasma Voyager had just left, what exactly had the spacecraft entered? Because interstellar space sounds empty, Voyager was about to show that it was anything but. The proof began with an event that happened before Voyager 1 had crossed the heliopause. In March 2012, the Sun erupted. A major burst of solar activity launched an expanding disturbance into the solar wind near Earth. Storms from the Sun can announce themselves quickly, far beyond the planets. The same disturbance becomes a traveler on an almost unimaginable route. Voyager was more than 100 astronomical units away. The shock had to cross billions of kilometers. It took roughly 13 months to arrive. That is longer than an entire season cycle on Earth, just for one disturbance to travel from the inner solar system to the spacecraft. Voyager was so distant that a violent event near the Sun became a delayed message from the previous year. NASA later traced the April 2013 plasma disturbance at Voyager to major solar activity from March 2012. That delay matters because by the time the disturbance finally reached Voyager in April 2013, the spacecraft was no longer in the environment where the eruption had begun. It had passed the August particle transition and continued outward for months. The Sun had launched the experiment while Voyager was inside. The experiment arrived after Voyager was outside, and that gave scientists exactly the kind of physical test they needed. A solar disturbance moving outward does not simply carry a label saying where it came from. It pushes on whatever plasma it encounters. A shock compresses charged particles and magnetic fields. In the right conditions, that compression can drive electrons in the plasma around Voyager into collective oscillation. That is what the plasma wave subsystem could detect. The instrument was not listening with a microphone. Space around Voyager contained far too little ordinary matter to carry audible sound through air. Instead, its antennas sensed changing electric fields produced by moving charged particles. The difference is essential. What Voyager detected was an electrical oscillation in plasma. Scientists could translate its frequency into a sound we can hear, but the scientific measurement was the frequency itself. NASA explicitly notes that the instrument detects plasma waves rather than ordinary acoustic sound. And frequency carries density. Plasma contains positive ions and free electrons. If electrons are displaced slightly from the ions, the electrical attraction between the separated charges pulls them back. Their momentum carries them past equilibrium, and they oscillate. The denser the electron population, the faster that collective restoring process can occur. So a plasma frequency becomes a kind of natural density gauge. You do not need to catch every electron. You can make the population ring and measure the pitch. That was the workaround Voyager needed. The direct plasma science instrument could no longer provide the decisive measurement. Voyager 1's plasma science instrument had stopped functioning in 1980 and was eventually turned off. leaving the plasma wave subsystem as the surviving route to infer density when strong plasma oscillations appeared. The spacecraft therefore depended on something completely outside its control. It needed the plasma to ring. On April 9, 2013, it did. Voyager's plasma wave instrument began detecting clear local oscillations. Over the following weeks, the frequency changed. The signal continued into May, giving researchers a sequence rather than a single isolated spike. JPL reported that the oscillations increased in pitch through May 22. This was important for two reasons. First, the oscillations were local. They revealed a property of the material immediately surrounding Voyager, rather than merely telling scientists that some distant radio source existed somewhere ahead. Second, the signal had a measurable frequency that could be related directly to electron density. The mystery was finally being converted into a number. Until this moment, the competing explanations had both survived because they could imitate parts of one another. A magnetic connection to interstellar space could let galactic cosmic rays enter while solar particles escaped. The true Heliopause crossing could produce the same particle pattern. The magnetic field direction had failed to separate those explanations cleanly. Density could. The outer heliosheath was expected to be extremely tenuous. The local interstellar plasma should be much denser. So the plasma wave signal was not merely another interesting observation to add to a list. It was a discriminating test. There was an expected state on one side. There was a different expected state on the other. And Voyager had finally obtained a measurement capable of choosing between them. The high plasma density inferred from these oscillations became the crucial evidence that Voyager was embedded in interstellar plasma. The engineering behind that moment had become almost invisible. The spacecraft had left Earth in 1977. Its electrical power came from radioisotope thermoelectric generators that had been declining gradually for decades. Commands and data had to cross more than 16 light-hours of space in each direction at Voyager's 2012-2013 distance. And the instrument now settling a fundamental question about the Sun's boundary was not the instrument originally intended to make the direct plasma measurement. It was a wave detector surviving from another era of the mission. That is what makes the test so revealing. The scientific requirement was simple to state. Determine the local electron density. The engineering route was anything but simple. Voyager could not repair its failed plasma instrument. It could not turn around It could not wait for a technician. It could not actively command the interstellar medium to oscillate. The only workable route was to exploit a physical consequence of an external shock, using hardware that still functioned after more than 35 years in space. Then Earth had to recognize what the signal meant. The solar eruption had become a probe inside the probe. It traveled outward. It struck the plasma. The plasma responded. Voyager measured the response, and scientists used that response to infer the environment. The causal chain stretched from the Sun to interstellar space and then back to Earth as radio data. A single measurement connected all three. There was also a subtle surprise hidden inside the timing. Crossing the Heliopause had not insulated Voyager from the Sun. The spacecraft could be outside the solar wind's domain and still be reached by disturbances launched by solar activity. Shocks generated by the Sun continued propagating into the interstellar medium and producing plasma oscillations around Voyager even after the crossing. So, interstellar did not mean untouched by the Sun. It meant the background plasma was no longer solar. That distinction would become increasingly important as Voyager continued outward. But in April 2013, the immediate question was narrower. What density had the plasma wave signal revealed? Scientists examined the oscillation frequency and converted it into an electron concentration. If the result matched the thin outer heliosphere, the August 2012 particle event could still be interpreted as an unusual magnetic boundary layer. If the result was dramatically higher, the magnetic field expectation would have to yield. For months, the missing density measurement had kept the crossing uncertain. Now the answer was encoded in a changing electrical tone, and when the number emerged, the disagreement stopped being close. Voyager was surrounded by plasma far denser than the material it had left behind. The next step was to quantify just how large that jump really was. The number that finally broke the stalemate was not a distance. It was a density. When Voyager 1's plasma wave subsystem detected the oscillations in April 2013, scientists could measure their frequency and use that frequency to estimate the number of free electrons surrounding the spacecraft. The result was roughly 0.08 electrons per cubic centimetre. That sounds almost impossibly empty. On Earth, even an excellent laboratory vacuum contains vastly more particles than that. A cubic centimetre is about the volume of a small sugar cube, and in the plasma around Voyager, that volume contained far less than one free electron on average. Yet in deep space, the comparison that mattered was not with Earth. It was with the plasma Voyager had just left. Near the outer heliosphere, the electron density had been only around 0.002 electrons per cubic centimetre. Move from about 0.002 to about 0.08, and the environment becomes roughly 40 times denser. The difference was enormous. This was the quantified contradiction the magnetic field could not explain away. If Voyager were merely sitting in a strange magnetic layer on the solar side of the heliopause, the local plasma should still have resembled the extremely tenuous heliosheath. It did not. The material surrounding the spacecraft had the density expected for the local interstellar medium. The argument now changed shape. Before the plasma measurement, scientists had two plausible stories. In the first, Voyager had not yet crossed. Magnetic field lines near the heliopause had simply opened a route that allowed heliospheric particles to escape and galactic particles to enter. In the second, Voyager had crossed, but the interstellar magnetic field near the boundary happened to remain aligned with the field inside. The density measurement strongly favoured the second. That is what makes a discriminating test different from another suggestive clue. A suggestive clue can fit several explanations. A discriminating test forces one of them to fail. The particle changes had told scientists that Voyager's magnetic access to the two particle populations had transformed. The plasma density told them what medium physically occupied the space around the spacecraft, and the medium was interstellar. Now the stubborn magnetic direction had to be reinterpreted. The magnetometer had not been wrong. The assumption attached to it had been too rigid. Scientists had expected a larger directional change because the interstellar magnetic field and the solar magnetic field were treated as distinct systems meeting at the heliopause. But fields in plasma are not static arrows printed on either side of a boundary. They are shaped by the moving material carrying them. As the local interstellar medium encounters the heliosphere, its magnetic field can bend and drape around the solar bubble. Near the surface, that distortion can make the external field direction resemble the field just inside more closely than a simple model predicts. So the missing turn became a clue about the structure of the heliopause itself. That is a deeper payoff than merely saying Voyager crossed. The crossing revealed that one of the boundary's most anticipated signatures was not universal. Nature preserved particle and density changes while weakening the magnetic contrast. The boundary was real. The expected geometry was incomplete. The density also changes how you imagine interstellar space. The phrase suggests emptiness beyond the solar system. But Voyager did not move from matter into nothing. It moved from one extraordinarily thin plasma into another plasma that was still extraordinarily thin by human standards, yet dramatically denser than the one behind it. The difference is physical enough to measure, and it has consequences. Plasma density affects how waves propagate, how shocks behave, how charged particles interact, and how the heliosphere balances pressure against the surrounding interstellar medium. The boundary, therefore, separates two regions not just by origin, but by measurable physical state. Inside, the solar wind has expanded across more than 100 astronomical units and become extremely rarefied. Outside, Voyager encounters material that belongs to the local interstellar cloud, through which the Sun is moving. One side is governed by an outflow from our star. The other is the medium our entire heliosphere is moving through. At the scale of a diagram, the transition is one line. At Voyager, it was a change in particle populations, plasma density, and pressure balance across an invisible interface. And the density measurement did something else. It turned the August 2012 event from an interesting possibility into a date that could be tested. The April 2013 oscillations proved that Voyager was in interstellar plasma, but April was more than 7 months after the permanent particle transition. During those months, Voyager had travelled hundreds of millions of kilometres farther outward. So one question remained. When exactly had the plasma changed? The April measurement alone could not answer that. Voyager might have crossed the particle boundary in August, and the true plasma boundary sometime later. If that were the case, August 25 would not be the Heliopause crossing. It would mark only a precursor. Scientists therefore needed evidence closer to the original transition. They went back through the plasma wave subsystem data, and there, months before the loud April signal, they found something weaker. In October and November 2012, Voyager had detected another episode of plasma oscillations. The signal was not as strong or as obvious, but its frequency still carried the same kind of information. The inferred density was already far above heliosheath values. That meant Voyager was in dense plasma only a few months after the August particle collapse. The gap had narrowed. Now scientists could compare the earlier density with the later April measurement. The density was not fixed. It appeared to increase as Voyager moved farther outward. That trend gave them a way to reason backward. If the plasma became progressively denser with distance, then extrapolating the measurements toward the Sun could indicate where the spacecraft first entered the denser interstellar environment. The inferred transition landed close to the date already marked by the particle instruments. August 25, 2012. Different measurements were now converging on the same event. The lower energy heliospheric particles disappeared permanently. Galactic cosmic rays rose. The plasma density later proved to be more than 40 times higher than the outer heliosphere. And when that density trend was traced backward, it pointed toward the same boundary crossing. This is why the historic conclusion did not depend on one dramatic reading. It depended on a causal chain. The particles identified the abrupt change. The plasma waves identified the surrounding medium. The density trend linked that medium back toward the earlier transition. Only then could the missing magnetic rotation be treated as a failed prediction rather than evidence against the crossing. The order matters. Scientists did not declare the field irrelevant because they wanted Voyager to be interstellar. They found a measurement that was physically harder for the alternative explanation to survive. Then the model changed. Voyager had crossed, but even that statement needed precision. It had crossed the heliopause, the boundary of the Sun's plasma bubble. It had not escaped every form of solar influence, and it had not left every structure that belongs to the solar system. Before we widen that distinction, one piece of the crossing still needs to be locked down. Humanity now knew Voyager was outside. The next task was to reconstruct exactly when it had stepped across an invisible boundary, months before anyone recognized it. Once the April 2013 plasma signal proved that Voyager 1 was surrounded by interstellar material, the most important question became historical. When had the crossing actually happened? The spacecraft had already travelled for months beyond the dramatic particle transition of August 25, 2012. By April, it was hundreds of millions of kilometres further from the Sun, so the dense plasma measured in 2013 could establish where Voyager was then, but not automatically where it had been 7 months earlier. The team needed to move backward through the evidence. That meant returning to the plasma wave subsystem data and looking for something weaker than the April event. The strong 2013 oscillations have been easy to interpret because the solar disturbance made the surrounding plasma ring clearly. Earlier data were less cooperative. The plasma had not been driven as strongly, and any useful oscillation could be faint. But in the records from October and November 2012, scientists found another episode. It was weaker. Its frequency still mattered. The oscillation indicated an electron density already much higher than the values expected in the outer heliosheath. That single fact pushed the possible crossing date backward by months. Voyager was not merely in dense interstellar plasma by April 2013. It had already been in dense plasma before the end of 2012. Now the gap between the plasma evidence and the August particle transition had become much smaller. But sometime before November was still not enough. The historic question was sharper than that. Did Voyager cross the Heliopause on August 25th, when the heliospheric particles disappeared permanently and galactic cosmic rays rose? Or did it cross a separate plasma boundary later? To decide, scientists looked at how the inferred density changed with time and distance. The April 2013 signal indicated a higher density than the earlier oscillations from late 2012. Voyager was moving outward continuously. So the measurements suggested that the interstellar plasma density increased as the spacecraft traveled farther from the heliopause. That gradient became a physical ruler. If density rose with distance outside the boundary, then the trend could be projected backward toward lower densities closer to the Sun. The question was no longer simply, what density did Voyager measure? It became, where does this density trend begin? And that is where different instruments started to converge. Trace the plasma density behavior backward, and the transition points toward late August 2012. Look at the energetic particle data, and one date stands out with exceptional clarity. August 25th. Before that date, Voyager had repeatedly experienced temporary changes. Solar-associated particles would decrease. Galactic cosmic rays would increase. Then the old state would return. After August 25th, the reversal stopped. The heliospheric energetic particles collapsed and stayed low. The galactic cosmic rays rose and stayed high. The spacecraft had crossed something permanent. Now plasma density was saying that the permanent particle transition had occurred at about the same place where Voyager must have entered the denser interstellar medium. Two different kinds of measurement were telling the same story. That matters because they did not depend on the same physics. The energetic particle instruments were tracking populations of charged particles moving through the magnetic environment. The plasma wave subsystem was inferring the density of the local plasma from its natural electrical oscillation frequency. One measured who could reach the spacecraft. The other revealed what material actually surrounded it. Agreement between them was much harder to dismiss than either signal alone. The magnetic field still had not made the dramatic rotation originally expected. But now that disagreement had lost its power to keep the crossing uncertain. The density evidence did not require the magnetic field to turn. It required the plasma surrounding Voyager to be interstellar. And it was... So the logic inverted. Earlier, scientists had treated the nearly unchanged magnetic direction as a reason to suspect Voyager remained inside. Now the particle and density measurements made the opposite conclusion stronger. If Voyager had crossed, then the field behavior had to teach us something new about the boundary. The missing rotation was no longer evidence that the heliopause lay ahead. It was evidence that the heliopause did not behave exactly as expected. This is the moment where the crossing becomes more than a date on a mission timeline. August 25th, 2012 was not chosen because it was convenient. It was reconstructed. The spacecraft itself had not announced, "Interstellar space begins here." Instead, scientists assembled the crossing from several physical changes that became meaningful only when compared across time. A permanent particle loss, a permanent cosmic ray increase, a later measurement of interstellar plasma density, an earlier, weaker plasma oscillation, a density gradient that could be followed backward, and a magnetic prediction that failed. Each piece removed one alternative. The result was a crossing that humanity recognized after it had already happened. Voyager had moved through the heliopause silently. No alarm sounded on board. No camera captured a line. the spacecraft simply continued transmitting numbers. On Earth, those numbers did not initially fit together. Then the April plasma oscillation supplied the missing variable. Once electron density entered the picture, old data changed meaning. That is an important scientific detail. A measurement can become more valuable months later because another observation reveals how to interpret it. The particle collapse on August 25th had always been in the record. What changed was the context around it. Before the density result, August 25th could be interpreted as the entrance into a magnetic transition layer. After the density result, the same event became the strongest marker of the heliopause crossing itself. The data had not changed. The explanation had... By September 2013, the Voyager team could make the conclusion public with a much stronger physical case. Voyager 1 had entered interstellar space in August 2012. But even that sentence needs to be handled carefully. The word entered makes the event sound instantaneous. Physically, Voyager encountered a boundary region shaped by magnetic fields, particle transport, plasma pressure, and structures capable of changing over time. There had been repeated precursor events. There had been temporary particle exchanges. There had been ambiguity. Then one transition became permanent. The exact date represents the best defined point in Voyager's measurements where the heliospheric particle environment gave way and later plasma evidence confirmed the new medium. So August 25th is not important because nature stamped a date onto the heliopause. It is important because independent measurements converged there. And that convergence transformed a mystery into a physical crossing. Now we can ask a different question. If Voyager had truly entered the material between stars, what was that material actually like? The answer begins with a correction to one of the most persistent images in space science. Interstellar space is often imagined as almost perfect emptiness. Voyager found something more interesting. It entered a medium thin beyond human experience, yet dense enough to ring, dense enough to transmit shocks, and dense enough to reveal that the nothing between stars has structure. Interstellar space did not feel empty to Voyager 1. That is one of the first assumptions the crossing quietly destroyed. Beyond the heliopause, the spacecraft was still moving through an environment so thin that, by terrestrial standards, it would qualify as an extraordinary vacuum. There was no atmosphere around Voyager, no wind you could feel, no cloud you could see. Yet the region was not nothing. It contained plasma. Atoms in the interstellar medium can be ionized, leaving free electrons and positively charged ions. Those charged particles were sparse, but they were numerous enough for Voyager's plasma wave subsystem to detect their collective electrical behavior. That was the important change. Inside the outer heliosphere, Voyager had been surrounded by plasma ultimately supplied by the Sun. It had expanded across tens of billions of kilometers and become extremely rarefied. Outside, the background material belonged to the local interstellar environment. The spacecraft had not crossed from matter into emptiness. It had crossed from one plasma population into another, and the new one was much denser. The strong plasma oscillations detected after the crossing indicated a surrounding medium roughly 40 times denser than the plasma Voyager had measured previously near the outer heliosphere. That contrast became one of the decisive reasons scientists concluded that the spacecraft had passed beyond the heliopause. The word denser can be misleading here. Imagine a cubic centimeter, roughly a tiny cube 1 centimeter on each side. Around Voyager, even interstellar plasma might contain far less than 1 free electron in that volume on average. There is almost nothing there by everyday standards. But physics does not care whether a density feels large to us. It cares about the difference between states. A large density increase changes the natural frequency of plasma oscillations. It changes how disturbances propagate through the medium. It changes the pressure environment acting against the heliosphere. And because Voyager could measure those consequences, the emptiness became measurable. The Sun itself helped reveal that structure. The solar shock that reached Voyager compressed and disturbed the surrounding plasma. Electrons began to oscillate collectively, producing the narrowband signal that allowed scientists to infer density. Later disturbances did it again. Solar eruptions continued sending pressure waves outward beyond the heliopause, and Voyager repeatedly detected episodes in which interstellar plasma rang in response. JPL reported multiple such shock waves, including one that continued while Voyager travelled hundreds of millions of kilometres farther outward. That gives us a more physical image of where the spacecraft had arrived. Interstellar space was not a silent void disconnected from everything behind it. It was a medium through which disturbances could move. A shock born near the Sun could cross the heliopause, travel through interstellar plasma, compress that plasma around Voyager, and create an electrical response detectable by antennas on a spacecraft launched decades earlier. The Sun no longer supplied the background plasma, but it could still disturb it. That distinction is subtle and essential. Crossing the heliopause means leaving the bubble dominated by the solar wind. It does not mean that every signal or disturbance from the Sun stops at the boundary. The heliopause is not a rigid shell. Energy can cross it. Pressure disturbances can cross it. Particles can cross it under the right conditions. What changes is which plasma controls the environment. Measurements from both Voyager spacecraft later reinforced this picture. Hotter, sparser plasma dominates inside, while colder, denser interstellar plasma lies outside, with some interaction continuing across the boundary. Voyager had moved into material that was already there before the solar shock arrived. The shock simply illuminated it. For a while, scientists had to wait for these intermittent disturbances, because strong plasma oscillations appeared only when the local medium was excited enough to reveal a clear frequency. Then the data became even more interesting. Years after the crossing, researchers identified a much fainter, nearly continuous plasma wave emission in Voyager 1's measurements. Instead of waiting only for large solar shocks to make the plasma ring loudly, the spacecraft appeared to be detecting a weak background tone associated with the interstellar medium itself. That gave scientists a way to follow density more continuously as Voyager moved farther outward. The signal emerged clearly in data beginning around 2017 and tracked changes in electron density over a much longer stretch of space. The measurement was delicate. The signal was much weaker than the dramatic oscillations triggered by solar disturbances. But scientifically, it changed the rhythm of the experiment. The interstellar medium no longer had to announce itself only during rare shocks. Voyager could begin tracing its structure along the spacecraft's path. And that structure was not perfectly uniform. Density changed with distance. The region beyond the heliopause was not a single featureless bath with one fixed number everywhere. Voyager was moving through variations in the local interstellar plasma. This is exactly why the original crossing measurement mattered so much. Before Voyager, the heliopause was something researchers modelled primarily from the inside. After Voyager crossed, one spacecraft could sample the medium immediately outside and watch how conditions evolved with increasing distance. The boundary now had measurements on both sides. That allows a more precise picture of what happened in August 2012. Voyager did not simply leave the Sun. It moved from a hot, extremely tenuous solar plasma into a colder and denser interstellar plasma environment. The particle populations changed. The density changed. The way waves moved through the surrounding material changed. Yet some solar disturbances continued to arrive. So the transition was both sharper and less absolute than the phrase "entered interstellar space" suggests. Sharp in composition and density, not absolute in influence. That is the pattern the data keep forcing us to accept. The heliopause separates environments without isolating them completely. The two sides interact, and that interaction is why Voyager could learn so much from being just outside. If the heliopause were a perfect wall, the Sun would stop communicating physically with the plasma beyond it. Instead, solar activity became a probe of that plasma. Every sufficiently strong disturbance that reached Voyager gave scientists another chance to measure the response. The spacecraft was effectively watching the sun strike the interstellar medium from the inside out. That is a remarkable inversion. For most of its mission, Voyager used sunlight, particles, fields, and instruments to study worlds controlled by the sun. Now the sun itself had become part of the measuring apparatus. Its disturbances travelled outward and exposed properties of material between the stars. But density was only one difference Voyager encountered after the crossing. The particle instruments had already shown another. Galactic cosmic rays became more abundant when the heliospheric particle population disappeared. That increase was not just another marker telling scientists where Voyager was. It revealed something about the enormous bubble behind it. For decades, Voyager had been travelling inside an environment that changed how much high-energy radiation from the galaxy could penetrate inward. Once the spacecraft moved outside, the researchers could compare the particle population there with the one the heliosphere had been suppressing. The difference was large. NASA's Voyager measurements indicate that the heliosphere protects Earth and the other planets from more than 70% of that galactic cosmic ray radiation. So the invisible bubble Voyager had just left was doing more than containing the solar wind. It was changing the radiation environment of the solar system. And that means the next consequence of the crossing points back toward us. Voyager did not merely discover what interstellar space contains. By stepping outside, it revealed what the heliosphere had been protecting the planets from all along. The crossing changed the meaning of the bubble behind Voyager 1. Before August 2012, the heliosphere had been the environment surrounding the spacecraft for its entire existence. Voyager was born inside it. Earth is inside it. Every planet is inside it. The solar wind had always been part of the background. Outside, the particle counts told a different story. Galactic cosmic rays became more abundant. These particles are not ordinary rays of light. They are mostly atomic nuclei and other charged particles moving at extremely high energies. Many have been accelerated by violent processes elsewhere in the galaxy, including supernova remnants and other energetic sources. They can cross interstellar distances. Then they encounter the heliosphere. The sun cannot stop every one of them, but its enormous magnetic bubble changes their paths. The solar wind carries magnetic fields outward, and irregularities in those fields scatter charged particles trying to move inward from the galaxy. NASA describes the heliosphere as a vast shield that reduces galactic cosmic radiation reaching the planets. That produces a measurable consequence. Cosmic ray intensity inside the heliosphere is lower than it is outside. Voyager had been watching that difference develop gradually for years. As the spacecraft moved farther from the sun, galactic cosmic ray counts generally increased. By 2012, the rise was accelerating. Then, after the final August transition, Voyager found itself in the much less modulated cosmic ray environment beyond the Heliopause. The comparison revealed something larger than the location of one spacecraft. NASA reported from the Voyager measurements that the heliosphere protects Earth and the other planets from more than 70% of the galactic cosmic ray radiation that would otherwise reach the region. That number changes the picture. The heliosphere is not a solid shield. It does not surround the planets like metal armor, and it does not absorb all dangerous radiation at one surface. It is a vast, moving, magnetic plasma environment. Its shielding comes from interaction. Incoming charged particles encounter the turbulent magnetized solar wind and the fields embedded in it. Their trajectories are scattered and modulated. Some still penetrate deeply into the heliosphere. Others are kept out or reduced in intensity. The protection is therefore statistical rather than absolute. But when the scale is more than 70%, statistical becomes consequential. Voyager could measure the difference because it had done something no instrument near Earth could do directly. It sampled both sides. Inside, the spacecraft measured cosmic rays after they had passed through the heliosphere's filtering influence. Outside, it could sample a population much closer to the unmodified local galactic environment. The spacecraft had effectively moved the detector through the shield. That makes the particle jump after the crossing more than a boundary marker. It is a before and after experiment, and the human meaning appears when we follow the consequence inward. Earth is protected by more than one layer. The heliosphere is the first enormous filter operating on the scale of the planetary system. Closer to home, Earth's magnetosphere deflects many charged particles. Then the atmosphere provides another powerful barrier before radiation can reach the surface. NASA describes these as successive layers of protection from space radiation. Standing on Earth, you live beneath all of them. Voyager had moved beyond the outermost of those protective environments. Nothing dramatic happened to the spacecraft at the instant of crossing, because Voyager was already engineered to operate in an intense radiation environment, and because the change was not a burst capable of destroying it. But scientifically, its detectors were now exposed to a particle population that had been partially suppressed throughout the spacecraft's previous journey. That is why the crossing tells us something about habitability without changing subjects. The same heliopause that Voyager crossed is part of the system controlling the radiation environment of the planets behind it. Change the heliosphere, and the cosmic ray environment inside can change as well. We already see this on a smaller timescale through the Sun's roughly 11-year activity cycle. When solar activity and magnetic conditions change, the modulation of galactic cosmic rays changes too. As the heliosphere changes with the solar cycle, the number of galactic cosmic rays penetrating it changes in the opposite direction. So the shield breathes, not as a rigid surface moving in and out like a balloon in a room, but as a changing plasma and magnetic system, whose ability to scatter incoming particles evolves with solar activity. Voyager had travelled through the far end of that system until there was no longer enough heliospheric modulation around it to hide the outside population. That gives the August particle jump a deeper meaning. The cosmic rays did not suddenly appear because the galaxy began producing more of them on that day. Voyager changed environments. The spacecraft moved beyond the region that had been altering their access. This distinction matters because it reveals what the heliosphere actually does. It does not merely mark where solar wind stops. It modifies what can reach the worlds inside. And that means the invisible boundary is connected to conditions billions of kilometers inward. Yet the Voyager data also prevent us from exaggerating the shield. More than 70% does not mean 100%. Galactic cosmic rays are measured inside the heliosphere. Some reach Earth. Their intensity varies. Earth therefore depends on additional defenses, including its magnetic field and atmosphere. The heliosphere is one layer in a nested system, not a perfect cosmic wall. That calibrated picture is more interesting than the simplified one. We live inside a cavity created by the Sun, and that cavity changes the energetic particle environment around us every moment. Voyager made that protection visible by leaving it. There is another consequence hidden in the result. If the heliosphere can modulate incoming galactic particles, then the shape, pressure, and magnetic structure of its outer boundary matter. The heliopause is not simply an abstract division between solar and interstellar. It is part of an active interface between two particle environments. On one side, solar plasma has spent years expanding outward. On the other, interstellar plasma and cosmic rays press inward. Voyager crossed where those regimes met. The sharp disappearance of heliospheric energetic particles and the rise of cosmic rays showed how abruptly particle access could change along that particular trajectory. But the spacecraft then revealed a limit to the word shield. Crossing outside did not place Voyager beyond every disturbance created by the Sun. Solar shocks continued to reach it. They crossed the heliopause and travelled through the denser interstellar plasma, sometimes making that plasma oscillate strongly enough for Voyager to measure its density. The April 2013 oscillations, for example, were tied to solar activity that had begun about 13 months earlier. So two statements that sound contradictory are both true. Voyager left the solar wind bubble. The Sun could still reach Voyager. The contradiction disappears once we separate background control from travelling influence. Beyond the heliopause, the surrounding plasma was interstellar. The energetic particle environment was far less shielded by the heliosphere, but a shock launched earlier by solar activity could continue propagating outward through that interstellar material. Think of leaving a harbour. Outside the breakwater, you are no longer in sheltered water. But a wave generated inside can still travel past the boundary. For Voyager, the heliopause marked a change in the medium dominating the environment. Not a magical point where every physical consequence of the sun became zero. That distinction forces the next step. We now know what Voyager left, a vast solar bubble that had been filtering much of the galaxy's high-energy particle environment. We also know what it entered, denser interstellar plasma where cosmic rays were more abundant. But if solar shocks could still overtake the spacecraft after the crossing, then interstellar cannot mean beyond the sun in every possible sense. The next measurement makes that clear. Even after humanity crossed the heliopause, the sun kept sending disturbances across the boundary after it. The heliopause was behind Voyager 1. The sun was not. That sounds contradictory only if we imagine the heliopause as a wall that blocks everything produced by our star. Voyager showed that it is not. The crossing marked a change in which plasma dominated the spacecraft's environment. It did not create a region where every solar disturbance suddenly vanished. NASA described Voyager, after the crossing, as being in a transitional region immediately outside the solar bubble, where some effects from the sun were still evident. The distinction begins with the solar wind itself. Inside the heliosphere, the background plasma flowing past a spacecraft is ultimately supplied by the sun. Beyond the heliopause, Voyager's density measurements showed that the background had become interstellar. That was the fundamental change. But a disturbance can travel through a medium that it did not create. A shock launched by solar activity can move outward through the heliosphere, reach the heliopause, cross into the interstellar medium, and continue propagating there. That is precisely why Voyager's plasma wave measurements were possible after the crossing. The large solar disturbance that left the inner solar system in March 2012 eventually reached Voyager in 2013. When it arrived, the shock disturbed the much denser plasma surrounding the spacecraft. The local electrons oscillated, and Voyager's plasma wave subsystem detected those electrical waves. The spacecraft was outside. The messenger was still solar. This gives the word influence two different meanings. One meaning is environmental control. Which plasma fills the region? Which particle population dominates? Which magnetic and pressure conditions define the local medium? By those measures, Voyager had crossed into interstellar space. The other meaning is transmitted disturbance. Can energy launched by the sun still move outward and affect the material around Voyager? Yes. NASA explains that the plasma wave subsystem senses waves in plasma generated by eruptions on the sun, and that these disturbances can influence the interstellar medium on both sides of the heliopause. So leaving the heliosphere did not mean entering a zone physically disconnected from the sun. It meant leaving the sun's plasma bubble while remaining close enough, in a cosmic sense, for disturbances from that bubble to continue arriving. The scale makes this especially striking. A solar eruption near Earth can affect the near-Earth environment within days. Voyager was more than 100 astronomical units away when the decisive disturbance travelled toward it. The journey took roughly 13 months. Imagine the event from Voyager's point of view. The sun erupts far behind you. You continue moving outward at about 17 kilometers per second. Weeks pass, then months. You cross the heliopause. The plasma around you changes. The particle populations change. Humanity still does not know with certainty that the crossing has occurred. And somewhere behind, the old solar disturbance keeps coming. Eventually, it catches you in interstellar plasma. When it arrives, it compresses that plasma enough to make the local electrons oscillate. The very sun whose plasma domain you have left becomes the thing that proves you left it. That causal reversal is one of the most elegant parts of the Voyager story. The heliopause did not stop the shock. Instead, the shock exposed the physical difference across the heliopause. Inside, Voyager had encountered much more rarefied plasma. Outside, the same kind of disturbance could excite oscillations at frequencies corresponding to a substantially greater electron density. The travelling disturbance acted almost like a hammer. The medium supplied the note, and the note revealed the medium. Later Voyager observations reinforced the same picture. Plasma wave events continued appearing irregularly in the data as disturbances reached the spacecraft. Those events allowed scientists to keep sampling the density of the interstellar material along Voyager's path. So the crossing was not followed by silence. It created a new way to listen. The spacecraft could now observe how solar activity interacted with interstellar plasma from the outside of the heliosphere. That is a measurement no detector near Earth can make from the same physical position. It also reveals why the heliopause should not be pictured as a perfect seal. Pressure can be transmitted. Fields interact. Energetic particles can cross under certain conditions. Shocks can continue outward. The boundary separates regimes, but the regimes remain coupled. A useful human-scale image is not a concrete wall. It is a shoreline. Cross from land into water, and the material around you changes abruptly. But vibrations, waves, and energy can still pass through the interface. The analogy is imperfect because plasma and magnetic fields behave differently from ordinary water and air, but the physical lesson survives. A boundary can sharply separate environments without preventing every influence from crossing it. Voyager made that distinction measurable across a boundary tens of billions of kilometers from Earth. And the Sun's ability to reach the spacecraft after August 2012 created another correction to the phrase interstellar space. Voyager had not entered the undisturbed galaxy. It had entered the local interstellar medium immediately outside a giant moving obstacle, the heliosphere itself. The plasma there was already being shaped by its encounter with the solar bubble. The magnetic field could be bent around the heliopause. Density could vary near the boundary. Solar shocks could propagate into it. Voyager was interstellar, but it was still close enough to the heliosphere to study the interaction zone from the outside. That is why NASA's description of a transitional region immediately beyond the solar bubble matters. Outside does not have to mean unaffected. It means the dominant medium has changed. This gives us a cleaner way to describe what happened when Voyager crossed. Before August 25, the spacecraft was embedded in plasma belonging to the heliosphere, even as interstellar particles increasingly found paths inward. After August 25th, it was embedded in interstellar plasma, even as disturbances from the Sun continued finding paths outward. The direction of exchange had not stopped. The identity of the surrounding medium had switched. That is the boundary, and it explains why several of the measurements appeared to disagree at first. Particles can cross before the spacecraft does. A shock can cross after it does. Magnetic fields can remain unexpectedly aligned across the surface. No single signal has to behave like a gate snapping shut. The heliopause is defined by the physical transition between plasma regimes, not by the disappearance of every connection between them. Voyager's experience therefore replaced a clean mental picture with a more useful one. The Sun sits inside a magnetic and plasma bubble. That bubble has an edge. The edge is real enough for particle populations and density to change dramatically, but it is permeable enough for the two environments to remain in conversation. And after the plasma density evidence settled the question of which side Voyager occupied, one old contradiction became impossible to ignore. The magnetic field had still barely turned. At first, that had been the reason to doubt the crossing. Now the crossing was secure, so the question had to reverse. Instead of asking whether the unchanged magnetic direction meant Voyager was still inside, scientists could ask what the unchanged direction revealed about the heliopause itself. The answer would become stronger when another spacecraft reached the boundary years later. Voyager 2 crossed the Heliopause in 2018, providing a second direct encounter with the boundary. Voyager 1 had not encountered a one-time accident. The magnetic mystery was about to survive a second crossing. The magnetic field had been the measurement that almost delayed the history of Voyager 1. Before the plasma density evidence arrived, the nearly unchanged field direction looked like a warning. Scientists had expected the heliopause to separate the magnetic field carried outward by the solar wind from the magnetic field of the local interstellar medium. A substantial change in direction seemed like a natural signature of the crossing. Voyager did not give them that clean signature. When the spacecraft passed the August 2012 particle transition, the magnetic field did not rotate sharply. Its behavior changed, and the field eventually became less variable outside the heliosphere, but its direction remained surprisingly close to the direction measured just inside. NASA later described that alignment as one of the major surprises of the crossing. At first, that result supported the cautious idea that Voyager might still be inside a final magnetic layer of the heliosphere. Then the plasma density measurement removed that escape route. Voyager was surrounded by interstellar plasma, so the magnetic result had to mean something else. One possibility was geometry. The interstellar magnetic field far from the heliopause does not have to retain exactly the same orientation when it reaches the Sun's enormous plasma bubble. The heliosphere is an obstacle moving through the local interstellar medium. As the external magnetic field encounters that obstacle, it can be distorted and draped around the boundary. That means Voyager could cross into interstellar plasma while still measuring a field that had been bent into a direction resembling the field on the solar side. Later analysis of Voyager 1 data supported the idea that the magnetic field immediately outside the heliopause was still being deflected by the nearby heliosphere. A 2015 study discussed by JPL found that the measured direction was slowly changing with distance, consistent with a field distorted near the boundary, rather than an undisturbed interstellar field. That interpretation turned the missing magnetic rotation from an embarrassment into a measurement of the boundary's influence. Voyager had not reached pristine interstellar space. It had reached interstellar plasma close enough to the heliosphere that the Sun's bubble was still shaping the field around it. The boundary, therefore, had a magnetic footprint extending beyond the point where the solar wind itself ended. But Voyager 1 offered only one trajectory through an enormous three-dimensional structure. A single crossing cannot tell you whether a surprising result is global or local. Perhaps Voyager 1 had simply encountered an unusual patch. Perhaps its particular path crossed the heliopause at a special magnetic geometry. Perhaps somewhere else around the solar bubble, the expected field rotation would appear. For years, there was no second spacecraft outside the heliosphere capable of answering that. Voyager 2 was still approaching. The twin probe had taken a different route through the outer solar system. Its path carried it toward another part of the heliopause, giving scientists a natural comparison that could never have been arranged after launch. Then, on November 5, 2018, Voyager 2 crossed. Its particle instruments recorded the same broad kind of transition seen by Voyager 1. Heliospheric particles dropped sharply, while galactic cosmic rays increased and remained high. Unlike Voyager 1, Voyager 2 also had a functioning plasma science instrument, so it could directly measure the plasma across the boundary. The measurements confirmed denser, colder interstellar plasma and the disappearance of the outward solar wind flow. That alone strengthened the physical picture built from Voyager 1. Then came the magnetic result. Voyager 2's magnetometer found that the field just outside the heliopause was again approximately parallel to the field inside. The surprise had repeated. JPL described the Voyager 2 observation as confirmation of Voyager 1's unexpected result. With only Voyager 1, scientists could not know whether the alignment was characteristic of the boundary or simply a coincidence at one crossing point. Voyager 2 showed the same basic behavior at a different location. That is a powerful kind of scientific escalation. The first spacecraft breaks the prediction. The second tests whether the break was accidental. It was not. The two Voyagers crossed the heliopause years apart, along different trajectories, and at different places on a boundary that itself changes with solar activity, yet both found magnetic fields inside and just outside that were more aligned than the simplest picture had anticipated. This does not mean every point on the heliopause must behave identically. Two crossings are still only two narrow paths through a surface vast enough to enclose the planetary system, but the second result changed the probability of the explanation. Voyager 1 no longer looked like an isolated anomaly. The alignment appeared to reflect something real about how magnetic fields are arranged near the heliopause, and that helps us reinterpret the original August 2012 confusion. Scientists had been waiting for a magnetic turn because they treated it as a marker of crossing from one field system into another. Voyager showed that the plasma boundary and a dramatic change in field direction do not have to occur together. The local field can preserve a similar orientation across the heliopause, even while the surrounding plasma particle populations and flow change decisively. That distinction is easy to miss in a simple drawing. Draw the heliosphere on a page, and the natural temptation is to colour the inside one way, the outside another, and put a sharp line between them. Real plasma boundaries carry memory of both sides. Fields bend, pressure compresses material, particles leak, shocks cross. The surrounding interstellar medium becomes perturbed before it reaches the surface and remains perturbed for some distance after it. Voyager 1 was not simply measuring the galaxy in its untouched state. It was measuring the galaxy immediately beside a giant magnetic obstacle. That is why the field direction could be both interstellar and distorted. The same measurement can tell you where the plasma came from and still reveal that the nearby heliosphere is reshaping it. The engineering makes the comparison even more remarkable. The two spacecraft were launched 16 days apart in 1977, but their planetary encounters sent them onto different paths. Decades later, those paths became two independent cuts through the heliopause. Voyager 2's working plasma instrument added measurements Voyager 1 could not make directly, while both magnetometers provided a way to compare the magnetic structure of the two crossings. The mission accidentally became a two-point boundary experiment lasting more than 40 years, and the answer it produced was subtler than the original expectation. The heliopause is a real physical divide. Solar wind plasma ends there. Interstellar plasma begins there. Energetic particle populations change dramatically there. But the magnetic field does not have to announce the crossing with a sudden geometric turn. That was the lesson hidden inside the measurement that initially made scientists doubt Voyager 1 had crossed at all. What looked like missing evidence became evidence of a more complicated boundary. Now only one conceptual trap remains before we can return to the opening question. Voyager 1 entered interstellar space in 2012. But it did not leave the solar system in every sense of that phrase. The heliopause is the edge of the sun's plasma bubble, not the outer limit of everything gravitationally connected to our star. Far beyond Voyager lies another scale entirely, and distinguishing those two edges changes what interstellar really means. Voyager 1 entered interstellar space in 2012, but it did not leave the solar system. Those two statements can both be true because they describe two different boundaries. The heliopause is a plasma boundary. It is the outer edge of the heliosphere, the enormous bubble created by the solar wind and the magnetic environment carried outward from the sun. Voyager crossed that boundary on August 25, 2012. Beyond it, the spacecraft was surrounded by interstellar plasma rather than the plasma of the solar wind. NASA places that crossing at about 122 astronomical units from the Sun. That is why Voyager 1 became the first human-made object to enter interstellar space. That gravity draws a much larger map. If we define the solar system as the collection of objects ultimately governed by the Sun's gravity, then the system does not end at the heliopause. Far beyond the planets, far beyond Voyager's 2012 crossing point, icy bodies can remain gravitationally associated with the Sun. The most distant of those populations is associated with the Oort cloud, and this changes the scale almost beyond recognition. Voyager crossed the Heliopause at about 122 astronomical units from the Sun. The inner edge of the Oort cloud is thought to lie thousands of astronomical units away. NASA gives a broad estimate of roughly 2,000 to 5,000 AU for its inner edge, and somewhere between about 10,000 and 100,000 AU for its outer extent. So the boundary Voyager crossed after 35 years of flight is not the final gravitational boundary waiting ahead. It is an inner frontier compared with the full scale of the Sun's distant domain. This is where the word interstellar becomes easy to misunderstand. It sounds as though Voyager crossed the last object belonging to the Sun and entered territory that belongs entirely to the stars. Physically, that is not what happened. Voyager crossed from solar plasma into the plasma between stars. It did not cross beyond every object gravitationally associated with our Sun. NASA explicitly distinguishes leaving the heliosphere from leaving the solar system under this broader gravitational definition. Much of what we call interstellar space can therefore occupy the same enormous volume that is still, in a gravitational sense, part of the solar system. The two definitions overlap. One boundary is controlled by pressure and plasma. The other is controlled by gravity. And the distances involved are radically different. You can feel that difference through travel time. Voyager 1 is escaping outward at about 3.5 astronomical units per year. At roughly that pace, NASA estimates that it will take about 300 years just to reach the inner edge of the Oort cloud. 3 centuries. That is not the time required to cross the cloud. It is the time required to arrive at it. The estimate for passing beyond the cloud's outer edge is on the order of 30,000 years. Now compare that with the journey to the Heliopause. Voyager launched in September 1977. 35 years later, it crossed into interstellar plasma in August 2012. That already felt like an almost incomprehensible duration for a machine built on Earth. Yet on the gravitational scale of the solar system, those 35 years carried Voyager only through the first kind of outer boundary. The next one operates on a timescale measured in civilizations. This is not just a larger number. It changes the meaning of distance. The heliopause is produced by an active competition between the solar wind and the surrounding interstellar medium. Its position belongs to a plasma system rather than a fixed gravitational shell. The Oort cloud is different. It is a theorized vast shell of icy bodies whose orbits remain associated with the Sun over immense distances. These objects are so remote that galactic tides and other distant gravitational influences can perturb them, yet the Sun remains central to their connection with the solar system. So one edge emerges from interacting plasma. The other fades into a gravitational borderland. There is no requirement that the two occur at the same place. Voyager demonstrated this distinction physically. At the heliopause, its particle environment changed. The surrounding plasma changed. The balance between heliospheric particles and galactic cosmic rays changed. Those were measurements of a medium, and together they identified the spacecraft's entry into interstellar space. Nothing comparable happened to the Sun's gravity there. Gravity does not switch off at 122 AU. There is no gravitational wall at the heliopause. The Sun's gravitational domain extends vastly farther, encompassing distant populations such as the Oort cloud under the broad solar system definition used by NASA. Voyager itself is on an escape trajectory rather than an orbit that will return it to the Sun, but that does not make the heliopause a gravitational escape surface. Those are different physical questions, and separating them resolves one of the most common contradictions in the Voyager story. How can a spacecraft be in interstellar space while still being inside the solar system? Because interstellar space describes the plasma environment outside the heliosphere, solar system under the broader gravitational definition describes a region extending much farther. There is no contradiction once the definitions are tied to the physics. The deeper consequence is that Voyager did not find one final edge. It found a hierarchy of edges. First came the planetary region, then the termination shock, where the supersonic solar wind slowed dramatically. Then the heliosheath, Then the heliopause, where solar wind plasma gave way to interstellar plasma. And far beyond that lies the gravitational architecture associated with the Oort cloud. This does not widen the investigation into a catalogue. It sharpens the original question. What happened when Voyager entered interstellar space? A particular physical regime ended. Not the sun. Not its gravity. Not every object belonging to the solar system. The thing that ended was the spacecraft's immersion in the sun's plasma bubble. That precision matters because it makes the achievement more real, not less. Voyager did not need to escape every last gravitational trace of the sun to make a historic crossing. It became the first spacecraft to place working instruments directly into the interstellar medium beyond the heliopause. For the first time, humanity could measure that environment locally with a machine that had begun its journey inside Earth's atmosphere. And it reached that environment while still carrying the physical history of the sun behind it. Solar disturbances could still arrive. The nearby interstellar environment could still bear the imprint of the heliosphere. The sun's gravity still extended enormously farther. Interstellar space was not a clean divorce from the solar system. It was the next physical layer. That prepares the final payoff. We began with an invisible crossing that did not look the way scientists expected. Solar particles disappeared. Galactic particles surged. The magnetic field stubbornly refused to provide the simple confirmation many expected. Months later, plasma wave measurements supplied the missing evidence, and the measurements converged on August 25, 2012. Now the language can finally match the measurement. Voyager did not cross the last boundary of the solar system that day. It crossed something more specific and directly measurable. It crossed the edge of the sun's plasma domain, and the final meaning of that crossing is hidden in the fact that nobody on Earth knew for certain when it happened. The spacecraft crossed first. Understanding had to catch up. At the beginning, Voyager 1 seemed to cross nothing. No flash passed the spacecraft. No camera saw a surface. No instrument produced a single unmistakable message saying that the sun's plasma domain had ended. Instead, the boundary revealed itself by subtraction. Particles that had accompanied Voyager through the outer heliosphere disappeared. Galactic cosmic rays became more abundant. The surrounding plasma later proved far denser than the plasma behind it. And one measurement that scientists expected to change dramatically, the magnetic field direction, refused to cooperate. That is what happened when Voyager 1 entered interstellar space. Not one event, a coordinated change in physical state. On August 25, 2012, at roughly 122 astronomical units from the Sun, the spacecraft passed the heliopause. The lower energy energetic particles associated with the heliosphere collapsed and did not return. Higher energy particles arriving from the galaxy rose and stayed high. The environment had changed permanently along Voyager's path. But permanence alone was not enough. Scientists still had to decide whether the spacecraft had crossed the true plasma boundary or merely entered an unusual magnetic layer near it. That uncertainty is what made the missing magnetic turn so important. The expectation had been simple. If Voyager moved from a solar magnetic environment into an interstellar one, the field should rotate noticeably. It did not. For a time, that contradiction kept the historic conclusion open. Then the Sun provided the experiment nobody could have scheduled. A disturbance launched months earlier travelled outward across more than 100 astronomical units. In 2013, it reached Voyager and disturbed the plasma around the spacecraft. The electrons began to oscillate. Voyager's plasma wave subsystem measured the frequency. And frequency revealed density. The result was not close to what the outer heliosheath should have contained. The plasma around Voyager was tens of times denser than the plasma it had left. That changed the problem completely. The spacecraft was not merely connected magnetically to interstellar space. It was immersed in interstellar plasma. Once that measurement existed, the old data could be read differently. A weaker plasma wave event from late 2012 showed that the dense environment had already been present only months after the particle transition. The density trend could then be traced backward. It converged on the same date the particle instruments had already marked, August 25th. The particles had identified the change. The plasma waves identified the medium. The density trend connected the two, and the magnetic field, instead of disproving the crossing, exposed a failed expectation about the shape of the boundary. That is the final scientific payoff. Voyager did not merely discover where the heliopause was. It discovered that the heliopause did not have to behave the way a clean diagram suggested. A boundary can be sharp in one quantity and subtle in another. Particle access can change abruptly. Plasma density can jump strongly. Magnetic direction can remain surprisingly similar. Solar disturbances can continue across the boundary even after the background plasma becomes interstellar. The two sides can be distinct without becoming isolated. That is why the crossing was so difficult to recognize in real time. Nature did not arrange every signal into one synchronized announcement. The measurements had to be understood causally. What disappeared? What increased? What medium surrounded the spacecraft? What prediction failed? Which remaining test could separate the explanations? Only after those questions were answered did the historic sentence become secure. Voyager 1 had entered interstellar space. And even that sentence now carries more precision than it did at the beginning. Interstellar does not mean beyond every influence of the sun. Solar shocks can still travel outward and reach the spacecraft. It does not mean beyond the full gravitational reach of the solar system. The distant Oort cloud lies vastly farther away. It does not mean empty. Voyager found plasma there, measurable through its electrical oscillations. And it does not mean untouched by the heliosphere. The nearby interstellar magnetic field and plasma still bear the physical consequences of meeting the sun's enormous bubble. What ended at the heliopause was something specific. Voyager stopped being immersed in plasma dominated by the solar wind. That is the crossing. A machine built on Earth moved from one star-controlled plasma environment into the material between stars and kept measuring. That achievement becomes stranger when you remember how little of the event was designed for the moment itself. Voyager had been launched in 1977 for encounters with the giant planets. The direct plasma instrument that would have made the boundary easier to identify was no longer useful. The spacecraft's power supply had been declining for decades. Its radio signal had to cross billions of kilometers before Earth could inspect the result. Yet enough of the spacecraft survived to solve the problem indirectly. Particle detectors showed the populations exchanging. The magnetometer preserved the contradiction. The plasma wave subsystem turned a solar shock into a density experiment. A failure in one instrument forced another part of the spacecraft to become more scientifically valuable. That is the engineering meaning of the crossing. Voyager did not succeed because every original capability remained intact. It succeeded because the surviving hardware could still answer the next necessary physical question. The spacecraft had no idea that August 25th was historic. It simply transmitted. That detail may be the most human part of the entire event. For months, Voyager was already beyond the heliopause, while people on Earth were still arguing about where it was. The machine had crossed before the explanation caught up. There is something appropriate about that. At the edge of a region no spacecraft had sampled from the outside, the first answer was not certainty. It was contradiction. The sun's particles disappeared, but the magnetic field stayed familiar. The spacecraft looked interstellar in one way and solar in another. Only later did the denser plasma reveal what had actually happened. So return now to the opening image. Voyager moves through darkness more than 18 billion kilometers from the sun. Nothing visible changes. No line slides beneath it. No wall passes the antennas. If you were watching only with a camera, you would miss the entire event. But the invisible environment is reorganizing around the spacecraft. The old energetic particles are draining away. Galactic particles are arriving more freely. The plasma ahead belongs to the space between stars. The magnetic field carries a geometry nobody fully expected. And somewhere far behind, a solar disturbance is already travelling outward, destined to arrive later and make that new plasma ring loudly enough for Earth to know what Voyager has done. The boundary was invisible. The consequences were not. That is what Voyager 1 really detected at the moment humanity first crossed the Heliopause. Not the end of the sun, but the point where the medium around us stopped being solar and became interstellar. And the final answer to our central question is quieter than the milestone sounds. What happened when Voyager 1 entered interstellar space? The universe around the spacecraft changed first. Human understanding followed. Tonight we began with a machine crossing a boundary nobody could see. Now the same image means something deeper. The darkness was never empty. The silence was never featureless. And the edge was never a line. Voyager 1 crossed into interstellar space when the plasma particles and governing physics around it changed, and for months, the only thing that did not know it yet was us.